Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Here begins the essay, Bernhard Riemann's on the hypotheses, which lie at the foundation of geometry, presented in 1854 and published posthumously in 1868, stands as a monumental achievement in the history of mathematics. It serves as a profound departure from the Euclidean paradigm, ushering in an era of geometric thought characterized by its unprecedented generality and its capacity to describe spaces far beyond the confines of everyday experience. This essay undertakes an evaluation of the claims advanced within Riemann's seminal work, examining its structure, its arguments, and its implications for our understanding of space, geometry, and the very nature of mathematical inquiry. We proceed through the work section by section, delving into Riemann's conceptual framework and evaluating its coherence and lasting impact. Section 1, defining manifolds and establishing the concept of n-dimensional space. Riemann commences his treatise by generalizing the notion of space, shifting from the familiar 3 dimensions to an abstract n dimensions. He doesn't simply extrapolate from lower dimensions. Instead, he establishes a definition of a manifold that prioritizes the intrinsic relationships between points, regardless of a presumed embedding in a higher dimensional Euclidean space. A manifold, as Riemann defines it, is a space in which the position of a point can be determined by assigning in independent quantities, or coordinates. He emphasizes the continuity of this coordinate system and the ability to express geometric relationships through functions of these coordinates. Riemann's claim is that this construct allows for a rigorous mathematical analysis of spaces beyond our immediate sensory perception. It goes beyond the limitations of Euclidean geometry, which presupposes a specific, fixed structure for space. The crucial claim is the liberation of geometry from its dependence on empirical intuition by grounding it in the abstract framework of manifold theory. This opens the door to considering spaces with potentially variable curvature, a radical departure from the Euclidean assumption of flatness. Riemann's insistence on intrinsic definition, instead of extrinsic embedding, is the bedrock of his groundbreaking approach. He aims to build geometric structures from the ground up, devoid of imposed external frameworks. Section 2, introducing the metric tensor and measuring length. Having established the concept of an n-dimensional manifold, Riemann proceeds to address the fundamental problem of measuring distances within such a space. Euclidean geometry relies on the Pythagorean theorem to determine the distance between 2 points. Riemann, however, seeks a more general method applicable to spaces with potentially non-constant curvature. He introduces the metric tensor, a mathematical object that encodes the local geometric structure of the manifold. The metric tensor, represented by the components g sub I, j, where I and j range from 1 to n, determines the infinitesimal squared distance ds squared between 2 infinitesimally close points with coordinate differences dx sub I and dx sub j as the sum of g sub ij times dx sub I times dx sub j over all I and j. This expression generalizes the Pythagorean theorem. Crucially, the components g sub ij are functions of the coordinates, indicating that the metric, and hence the notion of distance, can vary from point to point within the manifold. Riemann claims that this metric tensor provides a comprehensive and flexible means of defining distance in any manifold, regardless of its curvature. He asserts that the properties of the metric tensor fully characterize the intrinsic geometry of the space. This approach goes far beyond the rigid framework of Euclidean geometry, accommodating spaces with a far richer and more complex geometric structure. The introduction of the metric tensor constitutes a decisive step towards a truly general and coordinate invariant formulation of geometry. Section 3, examining the transformation of the metric tensor under coordinate changes. Riemann understands that a truly general geometric theory must be independent of the specific choice of coordinate system. Therefore, He explores how the metric tensor transforms under coordinate changes if we transform from one coordinate system, x sub I, to another coordinate system, y sub I. The components of the metric tensor will also change. Riemann derives the transformation law that relates the metric tensor in the new coordinate system to the metric tensor in the original coordinate system, and the partial derivatives of the new coordinates with respect to the old coordinates. The transformation law states, at g' sub kl, the metric tensor components in the new y-coordinate system are equal to the sum over I and j of g sub ij, the metric tensor components in the x-coordinate system, times the partial derivative of x sub I with respect to y sub k times the partial derivative of x sub j with respect to y sub l. This law ensures that distances, as measured by the metric, remain unchanged regardless of the coordinate system used. This coordinate invariance is a cornerstone of Riemann's geometric framework. It guarantees that the geometric properties of a manifold are intrinsic, independent of any observer's choice of coordinates. Riemann's claim is that this coordinate independency elevates geometry to a level of abstraction and generality previously unattainable. By focusing on quantities that remain invariant under coordinate changes, one uncovers the fundamental geometric properties of space itself. It represents a shift from a coordinate-dependent description of space to a coordinate-free, intrinsic description. Section for defining the curvature tensor and identifying invariants. The heart of Riemann's geometrical innovation lies in his definition of curvature. He recognizes that the vanishing of curvature is the defining characteristic of Euclidean space. In spaces with non-zero curvature, parallel lines can converge or diverge, and the angles of a triangle may not sum to 180 degrees. To quantify curvature, Riemann introduces the Riemann curvature tensor, a complex mathematical object that captures the local curvature properties of the manifold. The curvature tensor, denoted by IKLM, is derived from the second derivatives of the metric tensor components. Its precise formula involves a complicated combination of partial derivatives and products of the metric tensor and its derivatives. Riemann demonstrates that the curvature tensor vanishes identically if and only if the space is Euclidean. Furthermore, he identifies certain scalar invariants that can be formed from the curvature tensor. These invariants provide coordinate-independent measures of curvature. The most important of these is the scalar curvature, which is obtained by contracting the Riemann curvature tensor with the metric tensor. Riemann asserts that these curvature invariants completely characterize the local geometric properties of the manifold. They encapsulate the deviation of the space from Euclidean flatness. The introduction of the curvature tensor represents a profound advance in differential geometry. It provides a powerful tool for classifying and analyzing spaces with non-constant curvature. Riemann's claim is that the curvature tensor offers a complete and intrinsic description of the local geometric character of any manifold. Section 5, exploring spaces of constant curvature. Having developed the general framework for describing curved spaces, Riemann turns to the examination of particular examples. He focuses specifically on spaces of constant curvature. A space of constant curvature is one in which the curvature is the same at every point and in every direction. Riemann demonstrates that there are three types of spaces with constant curvature: Euclidean space, spherical space, also known as elliptic space, and hyperbolic space. Euclidean space has zero curvature. Spherical space has positive constant curvature and is topologically equivalent to the surface of a sphere in a higher dimensional Euclidean space. Hyperbolic space has negative constant curvature and possesses a geometry that is profoundly different from Euclidean geometry. In hyperbolic space, parallel lines diverge exponentially, and the angles of a triangle sum to less than 180 degrees. Riemann points out that each of these three spaces is characterized by a single parameter, the curvature k. In Euclidean space, k is 0. In spherical space, k is positive. In hyperbolic space, k is negative. He explicitly states the metric tensor components for each of these spaces, displaying how the geometry is encoded in the mathematical formulation. Riemann's claim is that these spaces of constant curvature represent the simplest and most fundamental examples of non-Euclidean geometries. He asserts that they provide a crucial foundation for understanding the more complex geometries that can arise in spaces with variable curvature. His exploration of these model spaces provides concrete examples of how his abstract mathematical framework can be applied to describe spaces with novel geometric properties. Section 6, considering the finiteness and infiniteness of space. Riemann then addresses the age-old question of whether space is finite or infinite. He emphasizes that his geometric framework allows for both possibilities. In Euclidean space, which has zero curvature, space is generally assumed to be infinite. However, in spherical space, which has positive constant curvature, space is finite but unbounded. One can travel forever in spherical space without ever reaching an edge or boundary. Riemann emphasizes that the finiteness or infiniteness of space is an empirical question, not a matter of logical necessity. He suggests that the curvature of space might be determined by the distribution of matter and energy within it. He speculates that the universe might be a finite but unbounded space with positive curvature. This is a radical departure from the Newtonian view of space as an infinite and absolute container. Riemann argues that the geometry of space is not a fixed and immutable property, but rather a dynamic one that can be influenced by physical processes. He proposes that careful astronomical observations might one day reveal the true curvature of the universe. Riemann's claim is that the question of the finiteness or infiniteness of space is ultimately a matter for scientific investigation. His framework allows for the possibility that space is finite but unbounded, a concept that challenged the prevailing Newtonian worldview. Section 7, exploring the connection between geometry and physics. Riemann ventures into the realm of physics, suggesting that the geometry of space might be intimately connected to the fundamental forces of nature. He observes that the metric tensor, which determines the geometry of space, could be influenced by physical fields. He speculates that the fundamental forces, such as gravity and electromagnetism, might arise from the curvature of space. This is a remarkably prescient idea, anticipating Einstein's theory of general relativity by more than half a century. Riemann acknowledges that his ideas are speculative and that much further research is needed to establish a definitive link between geometry and physics. Nevertheless, he argues that the connection between geometry and physics is a natural and compelling one. He suggests that the laws of physics might be expressed in terms of geometric quantities, such as the curvature tensor. This would provide a unified description of the universe in which geometry and physics are inextricably intertwined. Riemann's claim is that a deeper understanding of the relationship between geometry and physics could lead to a revolution in our understanding of the fundamental laws of nature. He anticipates that the geometry of space might play a crucial role in explaining the origin and behavior of the universe. This speculative element of Riemann's work illustrates his visionary approach to scientific inquiry. Section 8, examining the generation of metric relations within manifolds. Riemann delves further into the origins of geometric relations within manifolds, posing the question of how a metric, one that defines distances, actually arises. He recognizes that the metric tensor, the mathematical object that governs distance measurements, is not just an arbitrary addition to the manifold. Instead, it must somehow be determined by the intrinsic properties of the manifold itself. Riemann considers the possibility that the metric is generated by a fundamental underlying structure, perhaps one that is discrete rather than continuous. He suggests that what appears to be a smooth, continuous manifold at macroscopic scales might be composed of discrete elements at microscopic scales. The interactions between these discrete elements could then give rise to the metric tensor, which governs the larger scale geometry of the manifold. This is a remarkably modern idea, anticipating the concepts of quantum gravity and string theory, which propose that space-time is not smooth and continuous at the Planck scale. Riemann acknowledges that his ideas are highly speculative, but he believes that they are worthy of further investigation. He suggests that the search for a deeper understanding of the origins of the metric could lead to a profound revolution in our understanding of the nature of space and time. Riemann's claim is that the metric tensor is not a fundamental entity but rather an emergent property arising from a deeper, more fundamental level of reality. He proposes that the exploration of this deeper level could reveal the ultimate origins of geometry and physics. This represents a bold departure from the traditional view of geometry as a purely mathematical construct, suggesting that it is intimately connected to the physical reality of the universe. Section 9, discussing alternative hypotheses and the limits of empirical knowledge. Riemann concludes his lecture by considering alternative hypotheses regarding the nature of space, and by acknowledging the limits of empirical knowledge, he emphasizes that his geometric framework is not the only possible framework for describing the universe. He acknowledges that other geometries, based on different assumptions about the nature of space, might also be possible. He also acknowledges that our empirical knowledge of the universe is limited. We can only observe a finite portion of the universe, and our observations are always subject to error. Therefore, we can never be absolutely certain about the true geometry of the universe. Riemann urges caution in drawing definitive conclusions about the nature of space. He emphasizes the importance of remaining open to new ideas and new evidence. He suggests that future observations and experiments might reveal that our current understanding of geometry is incomplete or even incorrect. Riemann's claim is that scientific knowledge is always provisional and subject to revision. He argues that the pursuit of scientific understanding requires a spirit of intellectual humility and a willingness to question our most fundamental assumptions. This represents a mature and sophisticated view of science, acknowledging both its power and its limitations. Section 10, reception, legacy and impact on modern physics. Riemann's ideas, initially met with a mixture of incomprehension and skepticism, have had a profound and lasting impact on modern physics. His work provided the mathematical foundation for Einstein's theory of general relativity, which describes gravity as a curvature of spacetime. Einstein recognized the power of Riemann's geometry to describe the gravitational field and used it as the mathematical language of his theory. The Riemann curvature tensor plays a central role in Einstein's field equations, which relate the curvature of spacetime to the distribution of matter and energy. Riemann's concept of a finite but unbounded space has also had a major impact on cosmology. Many cosmologists believe that the universe is indeed a finite but unbounded space with positive curvature. As Riemann suggested, this model of the universe is consistent with current astronomical observations. Riemann's ideas have also influenced the development of string theory and quantum gravity, which attempt to unify general relativity with quantum mechanics. These theories often invoke extra dimensions of space, as well as the possibility that spacetime is discrete at the Planck scale, ideas that are reminiscent of Riemann's speculations about the origins of the metric. Riemann's claim is that his work has provided a crucial foundation for 20th century physics. He asserts that his ideas have transformed our understanding of space, time, gravity, and the universe. His legacy continues to inspire physicists and mathematicians today. In conclusion, Bernhard Riemann's On the Hypotheses which lie at the foundation of geometry is a work of extraordinary originality and insight. Its careful construction, from defining manifolds in terms of coordinates to the revolutionary introduction of the curvature tensor, built a solid platform for later geometries. His formulation of n-dimensional space, the introduction of the metric tensor to measure distances within curved spaces, and his exploration of spaces with constant curvature all represent groundbreaking contributions to mathematics. The essay's examination of the transformation of the metric tensor under coordinate changes underscores the coordinate-free nature of Riemann's geometry, highlighting its elegance and generality. Riemann's willingness to venture into the realm of physics, speculating on the connection between geometry and the fundamental forces of nature, demonstrates his visionary approach to scientific inquiry. He established that space's properties could be investigated geometrically. His suggestion that the universe might be finite but unbounded challenged the prevailing Newtonian worldview and paved the way for modern cosmology. While some of his ideas might have remained speculative during his time, their profound influence on 20th century physics, particularly on Einstein's theory of general relativity, cements Riemann's place as one of the greatest mathematical thinkers of all time. The essay has critically engaged with the claims presented, highlighting both their strengths and the visionary nature of his propositions. His work stands as a testament to the power of abstract thought to illuminate the fundamental structure of the universe.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.